So in this video, we're going to learn how to evaluate trig expressions for double angles and half angles using these 6 identities that are printed on the front of the foldable notes booklet. So in example 1, we're given that the cosine of theta is equal to root 5 over 5, and theta is between 0 and pi over 2 inclusive, which is in quadrant 1. So we know that theta is in quadrant 1, so sine, cosine, tangent, and the reciprocals of theta would all be positive in quadrant 1. In 1.1, we want to find the cosine of 2 times theta. That's a double angle. And cosine of 2x has 3 different identities that we can apply. So cosine squared minus sine squared, 2 cosine squared x minus 1, and 1 minus 2 sine squared x. Since all we know is the cosine of theta, then we're going to need to use this middle identity, 2 cosine squared x minus 1. The other 2 identities require cosine and sine, or just sine, and we don't know anything about sine yet. So we're going to use the identity 2 cosine squared x minus 1. And we're going to substitute the root 5 over 5 for the cosine of the angle. Then that gets squared and minus 1. So that's 2 times, and then we square the numerator, we square the denominator. Root 5 times root 5 is 5. And then in the denominator, 5 squared is 25. And then we have, to reduce that fraction to get 1/5, 2 times 1/5 is 2/5 minus 1, and we need a common denominator to subtract the fractions. So that'll be 5 over 5 for the 1, and 2/5 minus 5/5 is a negative 3/5. So the cosine of 2 times theta is equal to negative 3/5. Now, don't get confused about our given information that theta is between 0 and pi over 2 inclusive in quadrant 1. Right? The fact that this is negative tells us that the cosine of 2 times theta, that's double the angle, is actually in quadrant 2. Right? If we double theta from quadrant 1, we end up in quadrant 2 where cosine is negative. So next we want to evaluate the sine of 2 times theta. That's a double angle identity. Here's our double angle identity for sine, and that's 2 sine of x cosine of x. Now we know the cosine of the angle, we don't know the sine of the angle. So we're going to need to use our Pythagorean identity to evaluate the sine when we know the cosine. And remember that Pythagorean identity from our fundamental trig identities is sine squared x plus cosine squared x is equal to 1. So since we need to find the value of sine, we're going to subtract sine squared x from both sides, then we'll square root both sides to get cosine by itself. And since x is our angle in quadrant 1, we know that when we square root both sides, instead of a plus or minus, we're just going to have a positive. So the sine of the angle is equal to the positive square root of 1 minus the cosine squared of the angle. So now when we apply our double angle identity for sine, that's 2 times the sine, and the sine is the square root of 1 minus the cosine of the angle squared, and that angle's cosine is given as root 5 over 5. And then we're going to square that. That's all under the radical for our Pythagorean identity. And then we multiply that times the cosine of the angle, and the cosine is given as root 5 over 5. So now we're going to simplify. Underneath of the square root, we have 1 minus 1/5 when we square this fraction, and that's going to be 5/5 minus 1/5, which is 4/5, and that's times root 5 over 5. And then when we square root a whole fraction, we square root the numerator, we square root the denominator. So we have 2 times 2 over the square root of 5, and then that's times root 5 over 5. And our square root of 5 in the numerator and denominator cancel, and we're left with a positive 4/5. And so the sine of 2 times theta, so that's the double angle, is equal to 4/5. Okay, in example 3, we're going to evaluate the tangent of 2 times theta. So we need the double angle identity for tangent, and that's 2 tangent of x in the numerator, 1 minus tangent squared x in the denominator, which means we need to know the tangent. And if you recall the quotient identity for tangent, that tells us that the tangent of an angle is equal to the sine of that angle divided by the cosine of the angle. That's one of our fundamental identities, the quotient identity for tangent. And we know the cosine, that's root 5 over 5, that was given. And the sine we found was the square root of the quantity 1 minus cosine squared x, which we evaluated in problem 2 to get the square root of 4/5, which was 2 divided by the square root of 5. So to find the tangent of theta, we're going to need to take the sine, which was 2 divided by the square root of 5, and we're going to divide that by the cosine, square root of 5 over 5. And remember, dividing fractions means to multiply by the reciprocal. So we're going to take the 2 over root 5 and multiply that times 5 over root 5, and that's going to be 10 over 5, which is 2. So now we know that the tangent of theta is 2, and now we can put that into our double angle identity for tangent. So in the numerator, 2 times the tangent of x is going to be 2 times 2. Then in the denominator, 1 minus the tangent squared x, that's 1 minus 2 squared, which is going to be 4 over 1 minus 4, or a negative 4/3. So a question to consider now that we've evaluated the tangent of 2 theta using the double angle identity is, does the quotient identity apply if we were to have double angles? So would the tangent of 2 theta be equal to the sine of 2 theta divided by the cosine of 2 theta? And since we know the sine of 2 theta is 4/5, the cosine of 2 theta is negative 3/5, that would be taking 4/5 divided by negative 3/5, which would be 4/5 times 5 over negative 3. The 5's would cancel and we'd have a negative 4/3. So in this problem, it appears that that quotient identity would work with double angles.